I assume since there's nobody here but me, that everybody's going to be taking your exam in Brightspace. That being the case, I'm going to go ahead and get started with the next topic. Chapter 8, Chemical Composition. And the exam will be on time if it's submitted before midnight tonight. That is February 8th, 2024. Okay, so let me, let's see, I gotta open the PowerPoints first. Hold on a second. Okay. Get that share on the screen here. All right. So, chemical composition. This is the only chapter that's going to be part of exam 3. And the items that I would hand out in class, I'll show those to you. Okay. Of course, you're going to see all of these slides, right? These slides are in Brightspace. And then also look for review document for chapter 8. There it is right there. That's to give you practice. And there's also a key in Brightspace that I hadn't copied. I'm not going to hand that out. But the key will tell you which ones of these you get right and which ones you get wrong. If you treat this like an exam, then you can go through and find out where you're weak. If you can't figure out why you got one wrong, then that's what this document is for. This is work problems. Right? It's in my handwriting, and it takes each of these. It takes each of these review document problems and works them out by hand to show you at least one way to do them. There's usually more than one way to solve a problem, but when I created the document, that's how I did it. Now, you may see differences when I use the review document on review days for this chapter. You may see me work a problem different than you would see it in here. That doesn't mean it's wrong. It just means I've chosen a different approach. All right. So now we can get to chapter 8, chemical composition. Let's see. Get my hard copy out here. Yep. All right. So what do we mean by chemical composition? Excuse me. The problem in chemistry is that everything, an understanding of how chemical processes work requires an imagination. You've got to imagine the atoms and the molecules interacting with one another. That's at the microscopic level, and only for a few scientists in the world can we actually see that happening. Right? There's instrumentation that'll let you see individual atoms and molecules during a reaction, but that's on the cutting edge of research. And for most of the history of chemistry, we've been required to come up with an approach that works in the macroscopic world that we can manipulate ourselves and have some control and understanding of what's happening underneath at the microscopic level. So that's where we're headed with this. All right. The first concept is called counting by weighing. Right? the concept here is if you have, let's use an example. Say we have a jar of marbles. Right? You have marbles all the way down here, just full of marbles. We want to know how many are in that jar. Well, one approach is to just dump them out on the table and count them. But remember, these marbles represent atoms or molecules, things that you can't see. So we can't just dump them out on the table and count atoms. So we need an alternate approach. Well, if we are able somehow to take a subsample, small sample, and use an instrumentation and count the numbers of atoms or molecules, and at the same time determine the mass of that many, then we can calculate an average mass for each of the molecules or atoms in this container, and then use the total mass to determine how many atoms or molecules are in that container. That's where, when I first introduced the concept of dimensional analysis or using conversion factors, that's where we're going. That's what we need to solve this problem. So say if we have, if we pull out 10 of these marbles that represent our atoms, and we say for every 10 marbles, they weigh a certain number of grams, right? I think that's part of my slide. Let me keep going here. Well, we're going to use jelly beans. Okay. All right, let me go ahead with the marble analogy first. Let's say we have, we pull out 10 marbles or 10 atoms, and we have a way to measure their mass. All right, it's difficult to do, right? So you need somebody who's specialized in doing this for us. Then once it's done and we get a value, then we can run with it. So let's say we have, say 200 grams for that 10 marbles. Well, what's the average mass? Well, it would be 20 grams per marble. Okay? So that's the average mass of each one of these. Now, it doesn't have to be the exact mass of each one. They may vary, but at least for that sample, we've determined that the average mass of a marble is 20 grams. So let's say now we weigh the whole container, and we know the mass of the container, so we can subtract the mass of the container. Now we have the mass of all the marbles. Let's say the mass of those marbles is 3,000, let's say 30,000, 32,000 grams is the total mass, or 32 kilograms. It's a big jar. Now we want to convert that to the number of marbles. Well, remember, we have a conversion factor possibility here. If we put the grams on the bottom, remember this is in the numerator, denominator, they cancel. So we have so many grams, and then we have marbles on top. And remember what we covered in an earlier chapter, conversion factors are always equal to 1. That value is equal to 1 as a conversion factor. So we can flip it, and it's still equal to 1. So that's what I've done here. I just turned it over and put 20 grams here per marble. Grams cancel, and we can calculate the number of marbles. So let's see. 10 into that would be 3,200, and 2 of that would be 1,600. 1,600 marbles are in that container. Okay? What we've done is we've counted the number of marbles by weighing them. determine their mass. All right. So now for our jelly bean example. What's the mass of 1,000 jelly beans? They don't all have to be the same. We want to say we were going to weigh 10. If we want to know the mass of 1,000 jelly beans, so we're approaching the problem differently now. Now we know how many jelly beans are in there. There are 1,000 jelly beans in that jar. Suppose we weigh 10 of those jelly beans, and we find out that each one weighs this amount, right? 5.1, 5.2 grams, 5, 4.8, 4.9. They're not all the same. But what we need is an average mass. So if we take the average of those 10, what do we get? The average is 5 grams. Each of the jelly beans weighs 5 grams. So if we have 1,000 jelly beans, and we want to convert that to mass, we need jelly beans on the bottom. Say one jelly bean weighs what? One jelly bean weighs 5 grams. Right? Jelly beans cancel. 5 times 5,000 times 1,000 is 5,000 grams. Okay, so now we know how much that weighs. It's another way of using our conversion factor. Okay. Right, here's a problem where we're averaging the mass of different objects. If we have 2 samples and they contain different objects, an A on one side and B on the other, but we know that they contain the same number of objects. Okay. If the ratio of the sample of a mass in one to the sample of a mass in the other is a value, then we know that the ratio of the masses of all the individual ones in there is the same. So let's see if we got an example. Okay. Examples work better. All right, here's our marble thing. It's another possibility for marbles. Then we have a pile of marbles. I prefer a jar of marbles because a pile of marbles is going to roll everywhere. So let's put them in a jar. So that jar of marbles weighs 394.80 grams. That's the weight of the marbles in the container. Not the container, the weight of the marbles in the container. Right? As a practical matter, if you wanted to find out the weight of the marbles in the container, then you weigh the container first, put the marbles in it, weigh it again, and then subtract the weight of the container. Now you have the weight of the marbles. Then we're going to take 10 of those marbles out, and we determine that those 10 weigh 37.6 grams. Right? The question is, how many marbles are in that container? First, we need an average mass. Right? We determined that our average mass for a marble is 3.76 grams. And then the bottom calculation, 394.80. 394.80 grams is the total mass of our marbles. And our conversion factor is 3.76. So what they have done, 3.76. 3.76 grams per marble. What that calculation has done is it's taken this part and moved it over here. And that's over 1. So 1 times this is in the denominator, and this times 1 is in the numerator. And what we do here is we spread them out so that we can see the conversion factor. The way they've presented it there is not wrong. It's just you can't see what's being done, right? You can't follow the units, right? Because This side here, excuse me. This side here has grams, and that's grams. Grams cancels grams, and you're left with a dimensionless number, but they've put a dimension there. Where did that dimension come from? Well, it came from this calculation. Right, so that's what's not clear in this presentation. That's what's been done. So the grams cancel, leaves you with marbles. 3.76 divided into 394.80 gives you 105 marbles. So now we've determined that there are 105 marbles in that container based upon the total mass and the average mass of each marble, our conversion factor. All right. So we're going to take that analogy and move it over to counting atoms by weighing. Okay. This is an obvious fact. Atoms have very tiny masses, so scientists made a unit to avoid using very small numbers. We created a new unit, and then we're going to fix the value of that unit so that scientists everywhere will understand what that unit means when you say it or you write it. Okay? That unit is the atomic mass unit, AMU. So one atomic mass unit actually has an equivalence, right? One atomic mass unit is equal to 1.66 times 10 to the minus 24 grams. So it's very, very small. If we have determined a value to be so many atomic mass units, we can convert that to grams using this equivalence. Remember, conversion factors start with an equivalence. All right. So this is kind of jumping ahead here with the average atomic mass. The average atomic mass for an element is not a simple average, it's a weighted average. And I'm going to show you how to do that in just a few minutes. This slide, it jumps a little too far ahead. So let's hold that idea until I recall it for you. Here's our standard. Now our standard, excuse me, look at my hard copy. All right. I'm going to have to fill in some gaps here before we get to that. We need a standard, something that everybody agrees upon and everybody can use to standardize their the atomic mass unit. And here's the standard. Remember when we, I'm pretty sure we did. Hold on a second. Yes. When we talked about isotopes, an isotope is an atom of an element that has the correct number of protons, the atomic number, right? So there's our symbol, and we have the atomic number here, which is the number of protons. Then we have the mass number up here, which is the number of protons plus the number of neutrons, okay? And all we need to have a different isotope is a different mass number. And that mass number is based upon a different number of neutrons. So we can have carbon, which has 6 protons, and every carbon atom has 6 protons. If it doesn't have 6 protons, it's not carbon. So 6 protons, and the most abundant isotope has a mass number of 12. Right? So what is that? What do these mass numbers mean? Well, this means the number of protons. And this is one of the isotopes. Now, there's another stable isotope of carbon, which has an extra neutron. So it has a mass number of 13. The other isotopes of carbon are very, very small, minuscule amounts, and they're all unstable. They're radioactive. So we're just going to focus on these two. First, let's focus on this one. That one is the standard. We're going to say this is the number of protons. This is 6 protons plus 6 neutrons. And this doesn't say anything about the mass. What we're going to do is standardize it. We're going to say that this mass equals exactly 12. Atomic mass units with an infinite number of significant figures. That's our standard. Everything else is ratioed to that isotope. Okay? So even this one would be ratioed to that value. So the mass of this one is not going to be 13. It's going to be some fractional value that's based upon this standard. Now, why do we pick carbon as a standard? Well, for the longest time, oxygen was considered for the standard, and we would say oxygen would be equal to, or a mass would be equal to exactly 16 atomic mass units. There was a problem with that. Now, there was a reason for it, because most of the elements in the Earth's crust and on the Earth's surface, if they're combined with anything else, at least, especially the metals, are combined with oxygen. So oxygen was everywhere, in everything. But the problem is, to standardize oxygen, you need pure oxygen isotopes. And when we came up with this standard, gases were not easy to handle. So we looked around for a different standard, and we found that carbon is everywhere too, because carbon is it's in the atmosphere, it's dissolved in the waters, it's in every living thing on the planet, it's in a lot of rocks, right? So it's fairly easy to get pure carbon. So that's why we moved from this one to that one. All right. Now that we have our standard, we can ratio everything else to it. Well, when you look at the periodic table, you find that carbon here is given a value that's not 12. That's because it's a mixture of this isotope and that isotope and several other isotopes. But as long as we know the value of that, we call it molar mass. It's the average, the weighted average of a carbon atom. Now, here's a good question. If you take a sample of naturally occurring carbon and you physically divide it and divide it and divide it and divide it, get down to one atom, what's the probability, the chance that that atom is going to weigh 12.01 atomic mass units? The answer to that question is 0. There's no probability that you will ever find an atom with that mass. That's a weighted average, right? It includes masses of this and masses of that and masses of several other isotopes. This is a weighted average. It doesn't represent an individual atom. Well, actually, it does represent an individual atom when we're doing conversions. That's where it's useful. Okay. So let's use that value. This is the weighted average And I'm going to show you how to calculate a weighted average in a minute. But let's just assume that we've determined that for our sample of atoms of carbon, it's a mixture of different isotopes. And the average atom is 12.01 atomic mass units per atom. Right? So if we have 431 atoms of carbon, 31 atoms of naturally occurring carbon. So it's a mixture of isotopes. So we're not going to specify the isotopes. We want to convert that to atomic mass units. So we need a conversion factor. We have atoms down here and atomic mass units here, right? So what's the average, the weighted average atomic mass unit per carbon atom? 12.01. Atoms cancel, leaves us with atomic mass units. Now, I probably got it animated here, but I like to do it myself sometimes. Right, so we have 431 atoms times 12.01 atomic mass units. 3 significant figures. Remember, conversion factors are exact numbers. So these significant figures don't matter in the calculation. This one matters. 3 significant figures. So my calculator tells me one thing, and 5176. I round it off. 5176 atomic mass units for that many atoms of carbon. There we go. All right. So let me see. Yeah, cancel atoms leaves us with atomic mass units. Here we go. Come on. It's not behaving. Let's try it this way. There we go. All right. Let's do the same thing this time, only now let's use a different element. Aluminum. Say we have 75 atoms of aluminum. Okay. What value do we put here for the conversion factor? We don't use 12 because this is not carbon. So we go to the periodic table and we look at the atomic weight in that square with aluminum, and it's 26.98. Atomic mass units per atom. 26.98 times 7.5. And let's see, rounded off to 2 significant figures. I have, let's see, I got 202.3.5, and we rounded off to 2 significant figures. So it's actually like that. Well, that's the problem with standard notation. We're going to have to go 2.0 times 10 to the first. Oops. 10 to the third atomic mass units. Now, I'm not sure what the slide is going to tell us. Let's see what it says. All right. So it gives us the extra 2024. Right. That's kind of cheating, though, because there are only 2 significant figures here. But actually, you know what? That's correct. You know why? Because this is a counting number. Counting numbers are exact, right? Our example was number of pencils is a counting number. It's exact. So this does not limit the number of significant figures. 224 atomic mass units is perfectly legitimate. All right. Okay. Give me just a second. All right. There's a slide missing. I mentioned atomic mass units, the weighted average of atomic mass units. And excuse me. What I need is information that I don't seem to find. Just a second. I'm going to look it up. What I want to know is the relative abundance of carbon-12 and carbon-13. Right? I want to know what percent naturally occurring. So I'm going to take a minute. I think we have time. I'm going to take a minute and find those values. Just have to look it up here. Okay. All right. Carbon. Carbon isotopes. Isotopes of carbon. Okay. See if it'll give me relative abundance. Yep. Okay. So for carbon-12, the relative abundance is 98.9%. 98.9%. And the relative abundance of carbon-13 is 1.06%. Now, the rest of the isotopes are minuscule, plus they're radioactive. So I'm going to use this example without those. If this were our work responsibility, we would have to include every isotope naturally occurring. But I think we can come out to 2 decimal place accuracy without a problem. Okay. So the atomic mass units for this one would be 12. Right? The atomic mass units for that one, let me see. It's going to be a little bit different. So I got to go back and look at my, here we go. Let's see. Just a second here. 13, here we go. 13.003. 0034. How about that? This number of decimals doesn't matter because that's an exact number. It's our standard. Okay. So once we know this, the contribution to the overall is based upon relative abundance. It's kind of like calculating your grade point average. Right? You know that an A in a 4-credit course is worth more to your grade point average than an A in a 1-credit course, right? So we're using a weighted average. What's the contribution here? Well, we multiply this times its relative abundance, 989. And I'm using the decimal equivalent. I mean, you can say, what is 98.9%? It's 98.9 parts per 100. So if we take that fraction, parts per 100, we get this value. Okay, so that's why I'm using the decimal equivalent. All right, for this one, we want the equivalent of that one, which is 0.0106. All right, okay. Now, we multiply those out and then we add them together. And that gives us the weighted average mass of carbon. So let's take 12 times 0.989, which is 11.868 atomic mass units. And then 13.0034 enter in 0.0106 times. This is 0.1384. We have 4, 16, 1 and 9 is 10, 1 and 9 is 10, and 12. So there's the weighted average. Now, this only includes 2 isotopes. So it's going to be different than the one that you see in the periodic table. If we include all the isotopes, then this would be better expressed as an average 12.01 atomic mass units per atom. Okay, that's where the weighted average comes from, 12.01. All right, now we can move on. After going to all that trouble, you may or may not have realized that we don't have any instrumentation in our lab, in most chemistry labs, that can weigh so many atomic mass units for a container of atoms. Our balances don't work that way. We weigh grams. So one possibility is you can weigh the grams, then you can use the conversion factor of an atomic mass unit to grams and find out the number of atomic mass units. But that still doesn't help us. What we need is a value that will convert from mass to numbers for each element. Okay? And that's where the mole comes in. The mole is defined as the number of carbon atoms in 12.01 grams of naturally occurring carbon. Or it could also be 1 mole equals the number of carbon 12 atoms in exactly 12.000 gram sample. Okay? This would be if you're using that isotope. 12.01 would be if you were using the natural mix of isotopes, which would be more likely for somebody like me. So I don't have the instrumentation or the expertise to separate out, but this is the definition. And this is the useful application right here. Okay? Now, what's been determined is when we fix that number and say this is a mole, then we need to know how many atoms does that represent, right? And it's been determined, right, experimentally, that this Avogadro's number is 1 mole, and abbreviating a mole, you just drop the E, equals 6.022 times 10 to the 23rd objects. Or in this case, it would be carbon 12 atoms. So a mole is a number of things. It could be a number of atoms. It could be a number of ions. It could be a number of molecules. It could be a number of chickens. It's a mole if it's that number. All right. Now, how does that make it useful? Well, as it turns out, if you have a mole, 1 mole of carbon atoms, and notice I didn't say isotopes here, naturally occurring carbon atoms, if you have a mole of carbon atoms from the environment, then that mole of atoms will weigh 12.01 grams. Now we've got something we can hang our hat on. 12 grams of naturally occurring carbon is exactly 6.022 times 10 to the 23rd atoms. So when you look at the periodic table and you see that value for, let's see, aluminum was 26.98 atomic mass units per atom, right, for aluminum. If you have 26.98 grams of aluminum in your sample, then that tells you that you now have in your possession 1 mole of atoms. Right? That is much more useful. All right. Let's see. There's various versions of conversion factors that can be constructed from this equivalence. Right? We could construct an equivalence here. 26.98 grams of aluminum is equal to 1 mole. So there's your conversion factor. That many grams per mole. So what we're saying is, if you have a mole, if you have 2 moles, if you have 2 moles of aluminum, you want to know how many grams that is, then your conversion factor puts moles down here and grams up here, 26.98 per mole. Moles cancel, and 2 times 26.98 is approximately 52 grams. Without using my calculator, it's pretty close. No, excuse me, that's wrong. It's actually 54 grams. A little bit less than 54 grams. All right, so we can use these values now to do conversions. All right. Here we're just emphasizing the fact. When you know the mass, the atomic mass from the periodic table, that number could either be atomic mass units per atom. It's also equal to grams per mole of that atom. So gold is heavier. If you have the same number of atoms of gold as aluminum, you have actually almost 200 grams of gold. All right. Okay, let's take this example. Let's see. Yeah, we're doing good. Let's take this example. How many copper atoms in 63.55 grams? 63.55 grams of copper. And we want to know the number of atoms. All right. Well, what's the conversion factor? Well, you got to get rid of grams and leave yourself with moles. That's the only conversion that we know at this point. And then you can convert moles per atoms. Right? We know that 1 mole is 6.022 times 10 to the 23rd atoms. And we know that 1 mole of copper weighs what? 63.55. Right? So this divided into that is 1. And 1 times that is 6.022 times 10 to the 23rd atoms. Okay? All right. Let's try another one. Which of the following is the closest to the average mass of 1 atom of copper? All right, I don't know why I keep this slide in here because it's kind of silly, right? Is there any element that weighs that much in grams per atom? 63.55 grams per atom? No. You got to have a whole mole. So what that means is the smallest value in that list is probably the right answer, the last one. Right? And if you're pressed for time in a test and you get that kind of question, you can go straight to that answer. But what we're going to do is actually calculate the value. 1 atom of copper. Right? 1 atom of copper. And we want to find out how many grams that is. Well, we don't have a conversion from atoms to grams, but we do have moles to grams. Notice I put the moles on top because I want to keep it. Moles over here, this will be 63.55 grams per mole, right? So we need moles over here to cancel there, and we have atoms per mole here. Right? 6.022 times 10 to the 23rd atoms per mole. Moles cancel here, atom cancel there. Right? So 63.55 divided by 6.02 times 10 to the 23rd will give you 1.055 times 10 to the minus 22 grams. That's per atom. Okay? Yeah, there it is. All right. How about this one? Now we're going to change from copper to iron. Right? And you know your symbols, right? The iron symbol is Fe, Latin ferrum. Calculate the number of iron atoms in 4.48 moles sample of iron. So we have 4.48 moles, and we want the number of atoms. So we got to get rid of moles and leave us with atoms. All right, we know the conversion factor. Okay. So 4.48 times 10, 6.022 times 10 to the 23rd will give us 2.70 times 10 to the 26th, 10 to the 24th. 2.70 times 10 to the 24th atoms of iron. All right. Let's see, what if we have a sample of 26.98 grams of aluminum has the same number of atoms as how many grams of gold? All right, 26.98 grams of aluminum is actually 1 mole of atoms of aluminum. So what mass would be 1 mole of gold? Just look it up in the periodic table. AU is 197.00. All right, there it is. All right. Now, say we have 100-gram sample of each one of these elements: magnesium, zinc, and silver. Magnesium, zinc, and silver. We have 100 grams of each. Which contains the greatest number of atoms? We have 100 grams of each one. Which one contains the greatest number? Well, how do you get to 100 grams of atoms of each one? You got to collect enough atoms to give you 100 grams. So the lighter the atom, the more of them you need to make 100 grams, correct? So really all we need to compare is the molar mass, which is the atomic weight from the periodic table for each one of these, and that will tell us which one has the most number of atoms in that sample. Magnesium is 24.31. 24.31 grams per mole. Zinc, 65.38 grams per mole. And silver, 107.87, 107.87 grams per mole. Right? So which one has, if they're all weigh 100 grams, which one takes the most number of atoms to reach 100 grams? The lightest one. The lightest one is required more atoms. Okay. Magnesium. Okay, I'm going to leave that up there because I think I need it for the next example. All right. Now, in this case, we're given different masses of each of these. Well, let's see. Silver, zinc, and magnesium, and they get it reversed. So in this example, this is A, this is B, and this is C. Right? Okay. So what we've got here is different masses, 107.9 grams of silver, 107.9 grams. And zinc, we have 70 grams. Magnesium, we have 21 grams. 21 grams. Okay? We want to rank these in order of numbers of atoms from greatest to least. Right? So, since we only have 3, and the unit, the mole unit, is a counting unit. So if we find out how many moles, we can rank them in order of greatest to least. Well, since there are only 3, and I suspect that we don't even actually have to calculate the exact numbers, we could say which is equal to a mole, which is greater than a mole, which is less than a mole. Right? So if we got this many grams of that magnesium, is that greater than, less than, or equal to a mole? We've got less than the value needed for a mole, right? So this is less than a mole, less than 1 mole. 70, we have a mass that's greater than 1 mole. And for silver, we have exactly 1 mole. Okay? So now the greatest one is greater than a mole, right? Zinc. And then equal to a mole is silver. And then less than a mole is magnesium, right? So that would be B, A, and C, based upon our letters here. Now, this actually calculates for you, right? You can do it that way. It just takes extra time, and it's not necessary to answer the question. B, A, and C. B, A, C. Okay? That's the order from greatest to least. All right. Just a word on solving problems. If you haven't picked it up yet, just by solving these problems, when you solve a problem, and this works for just about any type of problem, especially word problems, what the authors are indicating here with where are you going, find out what's the end game. What is the question? There's always one question in every problem. Answer that question. Right? So, very often, the question that needs to be answered is at the end of the problem. So you go to the end of the problem and find the question. And then you work your way back up through the problem to do the next step, which is how you get there. How do you solve the problem once you know the question? Right? Some problems are really easy, one-step solutions, like a conversion factor problem, something like that. Other problems are more complex. They require several steps to get to the answer. And those steps will be elementary, that is, one calculation each, or one answer each, combined with the other answers to answer the final question. And then it's always important to do a reality check. Does the answer make sense? Is it reasonable? I mean, if you're just steamrolling along, working problems in this chapter, and I throw a problem at you that requires you to use techniques, skills that you learned in previous chapters, but you forgot those, you're only going to use the skills that you've acquired in this chapter, then you're probably going to get it wrong. So that's where the reality check comes in. Does the answer make sense? Right? If the answer, and this can be as simple as estimating the value, right? You have a calculation set up and you estimate the value, and then your calculator gives you a number that's pretty close to that estimate. Okay, so you know that you probably got a correct answer. Does it make sense? All right. So this value that you see in every square with the element symbol, and on our periodic table here, that value is at the bottom of the square of each element. That's known as molar mass because it represents the mass of 1 mole of those atoms. The molar mass of nitrogen, just look it up on the table, is 14.00672. Grams per mole of nitrogen. Okay? That's what the periodic table says. It's acceptable to round our values off to 2 decimal places. 14.01 grams per mole. Okay? And all our calculations are based upon 2 decimal places. That's the molar mass of an element. How do you get the molar mass of a compound? So for water, we have this expression for water. It has 2 hydrogens and 1 oxygen per molecule. Well, the molar mass would be, what is the mass of 1 mole of that formula? Well, when you have 1 mole of that formula, how many moles of hydrogen do you have? You have 2 moles of hydrogen, and you have 1 mole of oxygen. Okay? So, how many grams does 2 moles of hydrogen weigh? It's 1.01 grams per mole of hydrogen. So 2 times that would be 2.02 grams, right? And oxygen is 16 grams per mole times 1 equals 16 grams of oxygen. So that's 18.02 grams of water. Grams per mole of water. That's where that value comes from. Okay? You can do this with any formula, any correctly written formula. In this case, barium nitrate. Okay? Nitrate is a polyatomic ion. That's why we have to put a parentheses around it and a 2 here, because nitrate has a -1 charge. Barium is an alkaline earth. And when you combine barium in a compound, it's always 2+. Right? That's why you need 2 of these 2 minuses to balance. So now we've determined that that formula is correctly written. How do we get the molar mass from it? Well, 1 barium is 137.33. 137.33 grams per mole. This is barium. Nitrogen is 14.01 grams per mole. Right? This is times 1 mole. Right? If we have 1 mole of that formula, we're saying there's 1 mole of barium in it. For nitrogen, we're saying there are 2 moles of nitrogen. And for oxygen, we have 16 grams per mole times how many? 2 times 3 is 6. Okay? So this calculates out to 137.33 grams. This one calculates out to 28.02 grams. And this one is, let's see, 6 times 16 is 96. 96 grams of oxygen. They add them together. Right? So that's 5. That's 3. That's 14, 21. Carry the 2. 5, 6, 7, 16. 1 and 1 is 2. 261.35 grams per mole of the compound. All right. That's how we calculate it. All right. So why are we going to all the trouble of learning how to calculate molar mass? Because the same reason as always. Chemistry happens atoms and molecules interacting with each other. But measurements happen as mass. So we've got to take the mass, convert it to moles to understand the chemistry that's going on underneath. That's why we need molar mass. All right. This is just expressing the various ways that you can use molar mass to do conversions. And I find it easier to say, all right, if we have mass and we want to go to moles, we have mass, we want to go to moles. The conversion factor then will be grams on the bottom to cancel the mass and moles on the top to keep it. Okay? We want to go from moles to mass, grams. Now our conversion factor needs to be grams on the top, moles on the bottom. Cancel the moles, leaves us with grams there. Okay? It's much simpler to view it that way rather than to memorize formulas. This is more flexible. All right. So what's the molar mass of nickel 2 carbonate? Right? We learned how to name compounds. I'm pretty sure we did. Ooh. Yes, we did. Chapter 5, we learned how to name compounds. So this is a type 2 compound. It has a metal cation with a variable charge. So we have to say what it is. Nickel 2. So nickel has a 2+ charge. And the anion position is occupied by a polyatomic ion, carbonate, with a 2- charge. Right? How do I know that? Well, I memorized it. But you can look it up in the table of polyatomic ions that I give you in the review document and on every exam. Okay, so that's written correctly, just one of each. Nickel, like that. What's the molar mass? Well, now we need, if we've got 1 mole of that compound, how many moles of nickel do we have? Nickel is 58.69 grams per mole times 1 mole. Carbon, we've already done that one. Right? Carbon is 12.01 grams per mole times 1 carbon. And oxygen is 16 grams per mole times 3 carbons. Okay? So 3 times 16 is 48. And 12.01 and 58.69. We can add those together. 9 and 1 is 10, carry the 1. 7, 8, 10, 18, carry the 1. 6, 7, 11 grams per mole of compound. 118.7. Right, there it is. It's just that simple. All right. So now we can calculate molar masses of compounds as well as look up the elements on a periodic table. Okay, so in this case, we have equal molar samples of these 3 compounds. Equal numbers of moles. N2O, dinitrogen monoxide. It's also nitrous oxide or laughing gas. And we also have aluminum. Let's see, is that nitrate? Yeah, it's nitrate. Nitrate, need 3 of them. And potassium cyanide. The question is, if we have equal moles of this one, we have X moles of that one, we have the same number of moles of this one, we have the same number of moles of this one. We want to rank them at least to most number of nitrogen atoms in each sample. If we've got equal moles, we really only have to count up how many nitrogens. So this is 2 nitrogens, or 2 moles of nitrogen, or 2 times X, 2X nitrogens. Here we have 3X nitrogens, and here we have 1X nitrogens. Oops. Okay, so if we rank them from least to most, it's this one is number 1, this one's number 2, this one's number 3. So cyanide, aluminum, and nitrous oxide. Oh, excuse me. Least to most. KCN. Oh, okay. Yeah, this one, that one, then that. That's correct. All right. Let me see how many slides we got to go and how much time I've got to do it in. Okay, I think we can do this. We've got 100-gram samples of each of the following: water, nitrous oxide, C3H6O2, and carbon dioxide. Okay. We have 100 grams of each one of these. Okay. What I'm doing is I'm setting up my Henry Ford assembly line because I know what's coming. Rank them from greatest to least numbers of oxygen atoms. Right? Do we actually have to calculate the numbers of atoms? All we need is a counting value. And a counting value in these terms is the mole. So we really only need to go to moles of oxygen atoms, then we can rank them greatest to least. So first thing we need to do is calculate the moles of each compound. Grams on the bottom. Right? Cancel the grams, leave us with moles of compound. So what we need is the molar mass of each one of these. We did water earlier. Water is 18.02. N2O, right? 2 nitrogens, 14.01, and 1 oxygen, right? So this is 28.02. We're going to add this one with this one, and that's, let's see, 0.02, and this is 44.02. Okay? This one takes a little more work. Right? 3 times 12.01, right, for the carbons. 6 times 1.01 for the hydrogens, and 2 times 16 for the oxygens. And we have to add those together. Let me see. I can do that pretty quick here. 12.01 times 3 and 6.06 plus that, and then 32 plus that. So this is 74.09. Okay, and then carbon dioxide, 12.01 and 16 times 2 is 32. That's 104, 44.01. There we go. Okay, so we have the molar masses of our compounds that we're going to use to convert 100 grams of each into the number of moles of the compound. Okay, now we could go ahead and do that calculation. That would give us moles of compound, but that won't answer our question. What we need is a conversion to moles of oxygen. So what we need here is moles of oxygen. And down here, we have moles of compound. Okay? There we go. We need to know the ratio. Right? For every 1 mole of compound, how many moles of oxygen are there? Well, the ratio is embedded in the formula. For every mole of this compound, you have 1 mole of oxygen. For every 1 mole of this compound, you have 1 mole of oxygen. For every 1 mole of this compound, you have 2 moles of oxygen. And for every 1 mole of this compound, you have 2 moles of oxygen. Okay, so now we've canceled the grams. And we've canceled the moles of compound. And left ourselves with moles of oxygen. Okay, so all I have to do now is crunch the numbers. We're done with thinking. Now it's just pure math, calculator time. So 100 divided by 18.02 times 1 is 5.55 moles of oxygen. Then 100 divided by 44.02 times 1 is 2.27 moles of oxygen. Then 100 divided by 74.09 times 2 is 2.70. And 100 divided by 44.01 times 2 is 4.54. All right, now we can put them in order, right? From greatest to least. The greatest is this one. Well, this is number 1. This is number 2. This is number 3. This is number 4. Okay? And there are the calculations. Now, for this slide, I took it all the way to atoms of oxygen. You don't have to do that. To put them in order, you just need the relative numbers, moles. But we'll come up with the same answer. All right? And the order then becomes water, carbon dioxide. I think that's propionic acid. And laughing gas. Okay? That's why I call this Henry Ford, because the assembly line is I do the same thing, only with different values here, the same process, the same procedure on every one. And if I do it that way, then I keep myself from making mistakes. Okay. Let's see. All right. So let's go to the next one. You have lots of these types of problems in that review document. You also have available in Brightspace practice tests. I don't see them. I don't see the results. They're just for you to practice. You can take those tests over and over and over again if you want. So there are plenty of opportunities to practice. The more you practice, the better. Within the constraints of your lifestyle, whatever you have time to do as many as possible. How many grams of fluorine are contained in 1 molecule of boron trifluoride? Boron trifluoride. 1 molecule. Okay, we have 1 molecule of that. How many grams of fluorine do we have? Well, let's see. 1 molecule of boron trifluoride. Okay, we have 1 molecule. How many atoms of fluorine do you have? We have 3 atoms of fluorine per molecule. Right? So we got rid of molecules, now we have atoms. Now what we have to do, we can't get to grams without moles. So we have to convert atoms to moles. 6.022 times 10 to the 23rd atoms per mole. Right? That gets rid of atoms. Now we have the relationship of moles to grams for fluorine, which is 19, I believe. Yeah, 19.00. Okay, that's the thinking part. All done. Now we just crunch the numbers and find out which one of those values is correct. So let's see, we have 3 and 6.022 exponent 23 and divide by that one and then times 19. So I get 9.47 times 10 to the minus 23rd. Right. right there. I rounded mine off to 3 significant figures. We could probably keep as many as you want because that's a counting number. All right. Now we're going to shift gears a little bit. When a bench chemist goes into the lab and is given a sample, let's assume for the moment it's a pure sample of a compound. And he or she is asked to determine the relative composition of each of the elements in that compound. Typically, the answer that they will produce is percent by mass. Okay? Percent by mass. What that means is the mass percent of each element is so many grams, X grams of element per 100 grams of the compound. And I'll do that for each one of the elements. Right, there it is. Now, to illustrate the usefulness of this concept, you can use this information to determine a formula for the compound. And we're going to do that. Or you can take the compound and determine the relative mass percent of each element based upon the formula of the compound. Right? So our example here is iron 3 oxide. So let's say you have 1 mole of that compound. If you have 1 mole, what mass do you have? 1 mole of this compound will give you, and we have to determine the mass. So 2 times iron, which is 55.85. 55.85 grams per mole. And then 3 oxygens, 16 grams per mole. So this one is 55.85 and 2 times is 111.70 grams. And this is 3 times 16 is 48 grams. So we add those together and we get 159.70 grams per mole of the compound. Right? So that means we have 159.70 grams in 1 mole. Right? So how many grams of iron do you have in that 1 mole? We just kind of calculated it. 111.70. So for the iron, 111.70 grams of iron per 159 times 70 grams of compound times 100 will be the percent of iron in that compound. Right? 69.94%. And you can do the same thing for the oxygen. Or you can assume that it's 100%, just subtract this from 100, since there are only 2 elements here, right? And you subtract that from 100, and that'll give you the percent for oxygen based upon the formula. So we can do the same thing for this compound, which is the molecular formula for morphine. You just find out, all right, how much is the total mass that goes in the denominator. How much is the carbon in that 1 mole? Right, that'll be 12.01 times 17, and divide them times 100. 71.6% carbon in that formula. All right. Now, I think coming up is, let's see. All right, we've got 100 gram samples of each one. Rank them from highest to lowest percent oxygen by mass. All right, I don't have time to do that. Let me see if I've got it calculated. Yes. So here we have, for water, we have only 1 mole of oxygen, which is 16. And the total mass of the compound is 16 plus 2 times 1.01 times 100, right? We left out times 100. There should be 100 in here times that to be accurate. But the calculation gives us 88.81% oxygen. We do the same thing for nitrous oxide, same thing for propionic acid, and the same thing for carbon dioxide. And then we compare the values. And we find that percent oxygen by mass, water's the greatest, carbon dioxide's the next, propionic acid, and then nitrous oxide. Percent oxygen by mass, rank them from highest to lowest. All right. Now, I think this is the last topic. Yeah. What is an empirical formula? An empirical formula is the simplest whole number ratio of elements in a formula, in a compound. So, as opposed to, let's see, we have empirical formula, molecular formula. All right. Let's see if I skip something. I'm going to go back. It's not going to let me go back. All right. So we have empirical formula and molecular formula. This is the simplest whole number ratio of elements, whereas the molecular formula is the actual ratio of numbers of atoms in the formula. To illustrate, suppose we have this empirical formula, 1 carbon, 1 hydrogen. That could have been derived from the molecular formula of this one or this one. Either one of those would give you this formula, right? Because we can divide this one through by 2, right? This would be equal to that one with a 2 multiplier. This one would be equal to that one with a 6 multiplier, right? 2 times each one of these will give you that. 6 times each one of these will give you that. This is the empirical formula. Simplest whole number ratio of atoms in the formula. All right. So the reason we make that distinction is because we can determine the empirical formula from the percent composition by mass. But we can't go from here to here without another piece of information. And so we're going to do this one first. What's the empirical formula for this gaseous compound, carbon and hydrogen? It's found to contain 83.65% carbon. Let's see. 83.65% by mass of carbon. And it has one other element, hydrogen. So how much is the hydrogen? Well, we subtract that from 100, don't we? Right? If there are only two elements, they have to add up to 100%. So if we subtract this from 100, we get 5 here, we get 3 there, we get 6 there, and 1 there. Let's see if that's right. Add those together. All right, carry 1, carry 1, carry 1, 9 tenths. That's right. That's 100%. Okay, determine the empirical formula, the ratio of atoms, the ratio of moles of atoms in the formula. Well, we can't do that because percent is a dimensionless number. It's parts per 100. Now we know it's grams per 100 grams, and that's helpful. But still, we can't convert it to moles because it's not mass. So what do? Well, the ratio by mass is fixed, right? We know that from the law of definite proportions, right? Remember that one? The law of definite proportions says that a compound from any source will have the same ratio by mass of each of the elements in the compound, no matter where it's from. So let's say we have 100 grams of that compound. How many grams of carbon do you have now? Well, it's 83.65 grams per 100 grams. So if we have 100 grams, we have 83.65 grams of carbon and 16.35 grams of hydrogen. Now we can determine moles. This is the mass ratio. We're going to convert it to mole ratio. Right? So what we need is convert these to moles. Right? Grams on the bottom, moles on the top. Right? For hydrogen, it's 1.01, and for carbon, it's 12.01. Right? For this one, we're going to do step-by-step calculations. All right, so 83.65 divided by 12.01 is 6.965. 6.965 moles of carbon. And 16.35 divided by 1.01 is 16.188 moles. Okay, that's not a whole number ratio, right? So how do you get a whole number ratio? Well, the ratio is correct. For every 6.965 moles of carbon, you have 16.188 moles of hydrogen. We just need to find a whole number ratio. So the simplest way to do it is take the smallest one and divide by that value, right? For every ratio, if we divide each of the values of the ratio by the same number, it's still the same ratio. So this one's going to be 1. And what's that one going to be? Well, let me see. That was going to be about 2.3. Okay, we're getting closer. We got a whole number here, and we got 2 1/3 here. Yeah, actually 2.32. All right. So how do we get rid of that third? If you multiply this number times 3, 3 times the third is 1, correct? So if we multiply times 3, this will give us 3, and this will give us 7. Right? 3 times 2 is 6, and 3 times the third is 1, so 6 plus 1 is 7. So there's our empirical formula. Carbon is 3, hydrogen is 7. That's the simplest whole number ratio. Now, the actual formula could be, it could be 1, that could be the formula. Or if this is 2, it'd be C6H14. Or if this is 3, it'll be C9H21. Okay? Go to the next one. All right. That's what we did up to this point. And then we divided through by the smallest one. That gives us 1 and close. By this time, it's estimating. It's very close. Very close. We're trying to get to the whole numbers. So we're rounding and estimating in the process. So the empirical formula is C3H7. Okay. The molecular formula is the exact ratio of elements in the compound. So maybe there are 3 carbons and 7 hydrogens, and maybe they're not. Maybe there are twice that many of each one. So what we're looking for is this value right here. Okay. So if we continue with this same example, what we need now is to know the exact molar mass of the compound. If we know the exact molar mass, remember we calculated the molar mass based upon that value times the molar mass of the carbon, that value times the molar mass of the hydrogen. Well, if we do that for this one, it would say 3 times 12.01 and 7 times 1.01. What do we get? Right? So we have 12.01 times 3 and 10 grams per mole of the empirical formula, of that formula right there. Okay? So if we know the exact molar mass of the molecular formula and ratio it to this value, we can find out what that value is, right? Because if N is equal to 1, the molecular formula, the molar mass is going to be that value. If N equals 2, it's going to be twice that value. Right? 86 grams per mole. And there it is. 86.2 grams per mole is the molar mass. That means N equals 2. Okay. The other way to do it is say 86.20 ratio to 43.10 equals approximately 2. Now we can write the molecular formula. C6H14. Okay? That's how it's done. Now, we haven't told you how we came up with that formula, how we came up with that value, 86.2 grams per mole. You need a method that will give you the molar mass, and you don't have to know the formula. Right? And there are ways to do that. In this level course, we may not get to that point, but believe me, there are ways to get that value, depending on the nature of the compound. All right, let me see. We got 15 minutes, I think. Yeah, 15 minutes. Let me see how many more slides we got. This is the last one. Okay, so I think we got time to do this one too. This one takes a little more work because it has more elements in it, but it's the same procedure, step by step. We have adipic acid, which is one of the fatty acids, right? Everybody's got fatty acids in their bodies, and this may be one of them. So this particular fatty acid has 49.3% carbon, It has 6.9%. Let me see. I got to move something out of the way just in case. Yeah, it's okay. 6.9% hydrogen by mass, and 43.8% oxygen. Okay. Again, we can't do anything with that. What we have to do is assume 100-gram sample. So for a 100-gram sample, now we have 49.3 grams of carbon, 6.9 grams of hydrogen, 43.8 grams of oxygen. Now we can convert to moles. Okay, grams on the bottom, moles on the top. Okay, now oxygen is 16 grams per mole, hydrogen is 1.01 grams per mole, and carbon is 12.01 grams per mole. We just need to run those numbers. 49.3 divided by 12.01 is 4.110, 4.10 grams. Moles, excuse me, moles. Moles. 6.9 divided by 1.01 is 6.83. 83 moles of hydrogen. And 43.8 grams of oxygen divided by 16 is 2.74. 2.74 moles. Next thing, we take the smallest one and divide through everything by that one. So this is the smallest one, 2.74, 2.74, and 2.74. And that'll give us one here, of course. And let's see, 6.83 divided by is about 2.5, approximately. That's exactly, this is approximately. 4.10 divided by 2.74 is 1.5. Okay. Now, how do you get rid of a half by multiplying? You multiply by 2, right? 2 halves is 1. So if we multiply by 2, then 2 times 1 is 2, and a half times 2 is 1, so that's equal to 3. Times 2 here equals 5. Times 2 here equals 2. Okay? So that's the empirical formula. Carbon 3, hydrogen 5, and oxygen 2. Now, I assume we're headed for that one to find out what that was, but this is the empirical formula, and these are the steps we took, one at a time. Okay, 3, 5, and 2. Now, let's see, on the next slide, it's probably going to ask us for, yes, the molecular formula. All right. If we calculate the molar mass for this formula, I call it the empirical mass or the empirical weight, either one. Then what we have is 3 times 12.01, 5 times 1.01, and 2 times 16. Then we'll find out what that unit, what the mass is of that unit, 1 mole of this unit. So let's see, 312.01 times, and then 5.05 plus 32 plus, this is 73.08. 73.08 grams per mole of that formula. We're also told that the correct molar mass of the compound is 146. 146 grams per mole. So if we ratio the two, 73.08, that's approximately what? 2. So N equals 2, and our molecular formula is C6H10O4. There we go, step by step. There you go. 6, 10, and 4. And that's it. That's it for Chapter 8, Chemical Composition. Let me stop the share. There we go. All right. So we're done. And you guys are going to finish exam 2 tonight in Brightspace. And this is Thursday. So next Tuesday, we'll take that review document and work the problems, work several of the problems as time allows, to see if there are any kinks. Right? If you zoom in or show up in person, you can ask questions. That's it for today.